Hi everyone, welcome back to my Z80 computer series. I'm excited, I'm really excited. I've finally made a bit of a breakthrough with the VGA circuits. I've been struggling with this for so long. Finally last night I managed to get something sensible on the screen. It's not much, it's really basic right now, but I think it's kind of the barrier I had to break through to enable myself to see where I'm going with this and how I can get things to work. I could see all the pieces, I just couldn't see how to put it together. And I think I can finally see a solution. Might not be the best solution, but at the minute, right now, I just want to get something working. So what I'm going to do is I'm going to sort of talk you through it. Don't get too excited. If you've sort of seen the screenshot I posted in the community channel, that's all we're really going to see. But I'll try and talk you through the circuit that I've built, and then I'll show you what I've got on the screen. But before I do that, I just have an apology to make. I know somebody contacted me and asked me if I would send them a Tommy Prom circuit board, which I said that I would. Unfortunately, I've hunted around for them and I can't find them. I'm pretty sure I've got 2 more of these boards spare, which I'm happy to send out. I just can't find them. I've looked everywhere. I can't think where they could be. I have got an envelope with your name on it. It's got a stamp on it. It's all ready to go. I just need to find the boards. As soon as I find them, I promise I will get them in the post, and you're first on the list, so you will get one. I just can't promise when. So sorry about that. So let's jump in and take a look at this circuit. I think the way I'm going to try and do this is to sort of work backwards. So the final stage is the VGA output, where the RGB colours come into the connector. They come in through these resistors. We've probably mentioned before that the resistors are there to create a voltage divider. They're just to drop the voltage down to 0.7 volts maximum, because the signals that you send out through these wires need to be between 0 for like black and 0.7 volts, 0.7 volts for full intensity. So the resistors are there just to drop that voltage down a bit. The final output is being driven from this 74HC241 buffer. And the reason I'm using a buffer there is I've originally found that I couldn't get the VGA signal on the screen at all if I was outputting any color data during the blanking periods. So what I'm doing, the next chip over, is just an OR gate, a 74HC32. It's just a quad OR gate, and all I'm doing is I'm ORing together the horizontal blanking and the vertical blanking. Doesn't matter which way around they go, they're both just inputs to the OR gate. And if they're both low, then we get a low signal out of the yellow cable here, and it enables the buffer so the data starts flowing through it. I've got the blue line, the inputs are on this side. I've got the blue line tied straight to ground. I've got the green line tied straight to ground, and I'm just feeding my pixel data into the red line, so we should get red text out on the screen. This wire is coming from the other side of the circuit board. So over here, right at the top, this chip is a 74HC165. It's a shift register. It's a parallel to serial shift register. Takes 8 bits of parallel data in and shifts them out one at a time serially over this blue wire. It's connected to the Q output on the buffer chip. There are a couple of other control signals that go to that shift register. We've got clock, which is coming off my main clock, the 10 megahertz clock signal. It was connected directly to the clock, so that's essentially our pixel clock. And then we've got the load register. Sorry, we've got the load line. So this is telling it when it should load the next set of 8 pixels. And obviously we want to do that on every 8 clock counts. So I've got down here a 3 to 8 line decoder, Now I could have used a 3-input NOR gate, but I've used a 3 to 8 line decoder because I'm thinking I might want to do different things during the different 8 clock cycles that we have. So by using the 3 to 8 line decoder, it gives me a bit of capacity to do extra things later on as I start developing the circuit more. So basically the 3 inputs to that are connected to, maybe if I lift this up a bit, so they're connected to the first 3 horizontal counts of the VGA timing circuits. So those 3 lines will go low on, they'll all be low on every 8th count. So on count 0 they'll all be low, and on count 8 they'll all be low, on count 16 they'll all be low. So when that happens each time, we'll get the low signal out through here, and that will signal to the shift register that it needs to load the next 8 pixels. The input to the shift register is coming from these 8 lines here, these green lines, and they're just simply connected to the 8 data lines of this memory chip. Now I'm using an 8028C256, which is actually a 32K EEPROM. I'm using an EEPROM because at the moment we can't write to this circuit. We've not yet built any circuitry to share the memory with the CPU. So I needed something static, so something permanent that's in there that I can just do my testing with. I've actually loaded in here some data for a font. So it's a character set, and it's just loaded into the bottom of memory. I'm trying to think where I got that font from. I think it came from somebody's website called Jim Blimey, I think it is. But I think he may have taken those fonts from somebody else, so I'm not quite sure where full credit should go for that. But I've just stolen them, as I normally do. I mean borrowed. So that's the data that's in there. That's what I'm trying to display. Now, essentially the inputs for the memory chip are the address lines, which are the orange lines here. So depending on which address we set, we'll decide what set of data comes out through the data lines. Now the address lines are split into kind of two segments. The bottom 3 address lines, so that's address line A0, A1 and A2 are these 3 here, and then the next 4 up, which I'm not even going to bother trying counting, the next 4 lines up are over here. Now these 3, they do go to this little area here on the breadboard. That's not doing anything, that's just to extend the wires. These wires weren't quite long enough to reach over there, so I just linked some more across. But these are coming back. Again, I'll have to just lift up this board. This time, these ones are coming off of the vertical counts. Can't see that very well, can we? And I'm not using the bottom 3 counts. I've actually shifted them up by 2. And the reason I've done that is because I want to repeat every horizontal line 4 times. So by shifting these up a couple, that's the effect it has. We effectively just repeat every line 4 times. And I'm doing that because I'm using a 10 megahertz clock instead of a 40 megahertz clock, which is the particular VGA spec that I'm trying to follow. For 800 by 600 pixels requires a 40 megahertz clock, but we can cheat that by using a division of that. So I'm dividing by 4 by using a 10 megahertz clock. That essentially means we get only 1/4 of the amount of pixels across the screen. So instead of getting 800 pixels across the screen, I only get 200 pixels across the screen. I'm intending to scale that up in the future, but this is just for testing right now. So 200 pixels across is good enough for the moment. But that doesn't change the vertical count. Because we're meeting the specification for the timing of the horizontal count, that means we're also meeting the specification for the vertical counts kind of by default. So we still get the full 600 pixels on the vertical, but that would give us a distorted image. It would be like squashed. So by repeating every horizontal line 4 times, it has the same kind of effect. We'll get like a divide by 4 effect. So instead of getting 600 pixels on the height, we'll actually only get 150 pixels on the height, but it will give us square pixels rather than stretched pixels. Hopefully that makes sense. Yeah, so these 3 lines, the bottom 3 address lines, actually control the vertical position of the particular character that we're trying to draw on the screen. Now, characters on the screen are basically 8 by 8 blocks of pixels. So that forms one character. So where I've got my font, for example, the letter A might be displayed within this 8 by 8 pixel character. And for each character, I'm using these vertical addresses essentially to know where I am vertically within that drawing process of that 8 by 8 grid. So bottom 3 lines are the vertical position of each character. The next 4 lines up will define which character we actually draw. And I'm only going to be drawing 16 characters across the screen. I think that comes to 128 pixels, so we've got some spare room. But I'm just drawing 16 for now. I'm intending to double that up to 32 when I move forward. These 4 address lines are coming from this counter chip here. Now this is a 74HC163. I'm just using that because I've got a few of them lying around. I could have used a 161. I think there's a subtle difference between the 161 and the 163 in the reset timing. I think one is asynchronous reset and one is synchronous reset. I never remember which is which, and I don't think it would make any difference, but I'm just pointing out here that I'm using the 163. So these 4 lines are the counts out of that. Gets a little more complicated over here, and as we're working backwards, I will try to describe the resets part of the circuit first. So these 4 lines are going to count up from the number 0 to the number 15. That's 16 in total, from 0 to 15. And when it gets to I'm not quite sure if it's on the 15th count or when it rolls over to the 16th count, we get the signal out here called ripple carry out, RCO. And that's normally used to ripple out to another counter chip, so you can add some more bits on. It's just kind of to let the next circuit along know that this one's reached its final count and it's time for the next counter to start. But I've kind of borrowed that signal because that goes high after we've had our 16 counts. And I want to use that to reset this SR latch over here. But the SR latch is configured in a way that I need a low signal to reset it. And this gives us a high signal. Ripple carry out gives us a high signal. So I'm just running it through this inverter here to convert that back to a low signal, and that will reset this SR latch. That is the only purpose for this chip here, is just to invert that one signal. Now to set this SR latch, I'm using this wire here. It's kind of a little wire that I've broken off the back of the timing circuits, or the back of the timing circuit PCB, and I believe it's this chip here, although it doesn't really matter. But it's the chip that gives us the 264 count. It's when we're right at the end of the scan line. So essentially, right when we're about to start a new scan line. So I'm really enabling this SR latch at the beginning of every scan line. And what this SR latch is doing, there's an output from it. I believe that's usually described as Q. Incidentally, this is a NAND gate. What's that? 74HC00. It's a quad NAND gate, but it's configured in a way that it's acting as an SR latch. And if it really was an SR latch, we would label this connection up here as Q, because that's our output from the SR latch. And I'm using that to enable the character counter. So the character counter is only enabled when this SR latch is set. and it gets disabled when the SR latch is reset. So it's enabled at the start of every scan line, and it gets disabled after it's drawn 16 characters. So that works quite nicely. And I think that was kind of the final piece of the puzzle to try and work out how to get that working. It's not difficult, it's just for some reason I struggled with it. I think I just made mistakes, and then I was struggling to really diagnose and understand the mistakes, and it's just constant fiddling with it. I finally realized what I had wrong, and it was essentially I just had these address lines wrong, and I also had them mixed up with the ripple carry out. Confused myself and thought the ripple carry out was over this side, and it's not, it's over this side. It's just silly mistakes like that. And it was just when I was looking at, I was playing around with another timer, I thought I want to try and understand this timer. So I set another one up, started playing with it, and then I realized that I've got the wires in the wrong places. Sorted that out, turned it on, and boom, the image came on the screen. I was so ecstatic, you wouldn't believe how excited I was last night to finally see that after all of that trying, all of that effort and getting nowhere, and then finally the output came. Yeah, made me feel really good. There's a long way to go. This is very basic, but it feels like this gives me a good grounding place to start with to build off of this, to build other circuits or improve this circuit. Let's power it up and let's take a look. What do we get on the screen? Well, we got nothing because I'd knocked a couple of the wires out. I don't know if you spotted that when I was rambling on. I'd knocked some of the wires out. So let's try again. Boom, there we go. So this might look a little strange, but hopefully you can recognize that these are actually some real symbols. This is a slightly strange font. I think I didn't intend to pick this one. I was a little confused on how the fonts were organized, and the one I thought I was picking is not the one I got. But this particular font is a little strange. It would make a lot more sense if you could see the whole character set. But some of these symbols look a little bit strange, but they are just to fit in with the style of the rest of the font. Now this is actually an exclamation mark, but it's a really fat one. It's a really wide one. When you see a whole load of them in a line like that, they don't look like exclamation marks, but you kind of imagine it is. It's a long line with a dot at the bottom. It's just stretched fat. Double quotes, the hash symbol, $sign, percent sign, ampersand. I believe this is a single quote or an apostrophe. Round braces, so we've got the left and the right brace. An asterisk, a plus symbol, although again it's a little odd. It's got like this extra pixel here, but I believe that's deliberate. I think that's the design of the font. This I believe is a comma, and a minus sign, a full stop, and a forward slash. Now they're really big on the screen because this is like half resolution. This is only 16 characters across, and I think in the same space I'm intending to put 32 characters across on the screen. Now that was my plan, but as I'm looking at it now, I'm thinking that's a lot of wasted screen that we've got over here, so maybe I should rethink those numbers. It's just that 32 works out really nicely when you're trying to load data from memory. So I might stick with that for a start, but it will we've certainly got some room to expand it and make some changes. I'll have to see how flexible I can make the whole circuit. Unfortunately, that is about it, but what we could do is just quickly, just for a little bit of fun, we could try some different colours. So that's blue. That's green. There's yellow. There's cyan. Trying to think which ones I missed. I think I've missed a few, but I mean, you get the idea. We could actually also change the background. Let me think here. I think if we tie one of the lines high, we'll change the background. Yeah, so there's there's a red background. Now I'm essentially outputting red all the time, so any other colours I'm outputting are getting kind of laid on top of that, which is why the text has changed to white. But that was actually an interesting test, because it shows me, well, I suppose it's not really a good test, is it? Because I just permanently tied the line high. I was thinking there's no black gaps anywhere, but that's not a good test at all. We need real timing driving everything. Okay, well, that's about it. What I sort of thinking the next stage, I really need to figure out how we can draw the next set of characters. I mean, I'm just repeating the same characters over and over on the screen. So I think we've got this chip here to count horizontally for the characters. It'll count 16 characters across. So I think what we need to do next is count vertically how many characters we want to draw vertically. And those vertical character counts, would probably feed into the next address lines. I think there's some on this side and some on that side, so I'm not sure exactly which address lines, but I'm just pointing generally at this chip. The higher address lines would come from that vertical counter. And of course that would probably also need its own SR latch to tell us when we should be counting vertically. So I think that's what I'll do next. I'll try and build the vertical counter. So I hope that was of some interest. Thanks for watching, and I'll see you in the next one.